Good morning. Um, we are making our way through chapter 11. We've looked at angular momentum. We've talked a lot about angular momentum, how we can go in and do calculations of angular momentum, how angular momentum is conserved. And now, in addition to linear momentum and linear momentum conservation and energy conservation, we can now solve problems using angular momentum conservation. So it's going to be our third conservation law. And then what we had talked about at the end of the last class was that the torque can be written by this cross product, and there it is. And so we've got this new vector definition for the lever distance, and we've always had forces as levers. And so we kind of have a new definition for lever distance in terms of a vector, and that's going to allow us to calculate torques as a vector quantity. So here's practice. Suppose that we have a lever vector, and it's in the xz plane, and that it's given by this. So the lever vector has components of 1.2 meters in the x direction and 1.2 meters in the z direction. So that's where that is located. Calculate the torque given that the force is 150 newtons and the force is in the direction of x. So let's see what this would look like. Now, here is an xz plane. Now if this is x and z, then y is into the board, I think, right? I'm pretty sure. Yeah, so the y direction is pointing into the board. Go back and look at your math books or your physics books and look at those three-dimensional x, y, z coordinate systems. Oh, and I redrew it down here too. So if this is the direction of x, this is I, and this is the direction of y into the board. We use an x to represent that. And then the direction of z is here. So the way cross products work, the way right-handed coordinate systems work is that the x unit vector cross the y unit vector equals the z unit vector, and then we can cycle through. So x cross y equals z, y cross z equals x, z cross x equals y. Now in the book's notation, that would be I cross j equals k, j cross k equals I, k cross I equals j. So you just cycle through those three letters. So let's take a look and see how this cross product is going to work. So in general, the lever distance could have components x, y, z. It turns out that we have two of those components, but we don't have anything in the y direction. And so the y I'm giving a 0, and the x and the z I put in 1.20. I've also, this is a simple enough problem, it's not too difficult to draw that out. So I drew that on the xz coordinate system over there on the left. Now the force, they told us, is exclusively in the x direction. So here is the point where the force is being applied. Here is the lever distance. And the force is going to be entirely in the x direction. Now the r vector has components z and x. Which one of those lever distances are we interested in if we want to come up with a torque calculation? Now this lever distance doesn't really provide any torque because it's in the same direction as the force. So that's not going to make a contribution, but this component will. So what we're guessing is, when we do the cross product, it will be exclusively the lever distance in the z direction that will provide us a torque. Let's see what happens. So these were the components for R, these are the components for F, And now I'm just going to follow the rules that we had set up. Torque could be, we could have torque components in the x, y, and z, and this was the formula. So I mean, I could read them all off again, but I think it's probably more useful just to stare at that. So what's happening here is, well, a lot of these were zeros, and that's good. If you're doing cross products and a lot of these components become zeros, that can always simplify your life. So these two were zeros, as well as this component here. Now what that meant was, when I looked at the y, y was equal to 0, so that one went away. And where else do we have a y? Oh, we actually have it here too. So I didn't get those crossed out. Okay, so when y is equal to 0, that term goes out. Y is equal to 0, that term goes out. Here, the force y and force z go away. So force y I can cross out. Force y I can cross out. So that bottom one's gone. The top one's gone. And then force z is also 0. So the only product left, notice we had to do 1, 2, 3, 4, 5, 6 different products, but only one of them was non-zero. So that really helped simplify our problem a lot. So what it comes down to is only the z component, that's what we talked about, of the lever is going to apply, and the force is only in the x direction. Okay, and so it's going to be that 1.20 meters of z times the 150 newtons of force, and that's what, 180, something like that, 180 newton meters of torque. Now notice, the only component of torque is in the y direction. So let's see, if this is the y direction into the board, I could put my thumb in the direction of that y-axis and say a positive torque would go in this direction, a negative torque would be back the other direction. This looks like a positive torque because it's going to tend to rotate the system this direction around the y-axis. And so, yeah, we were able to look at the diagram, I hope, and kind of predict where the torque would be, and it seems to match up with what we calculated when we did the cross product. Okay, so a continuation here, the torque turned out to have a component in the y direction only. Let's look at, oh good, we got the vector diagram right here. So how are we to use the vector diagram when we're calculating torques? Now here's an alternate way to calculate the torque. What we can do is do a vector diagram, and notice I picked up the r, I brought it over to my vector diagram. I picked up the f, I brought that over, and I placed them so that they're both extending away from the origin. That's the angle between them. So theta right here is the angle between r and f. So if I came back up to this picture, theta is in here between those two vectors. Now, we talked about, yeah, so by the right-hand rule, this is in the positive direction. Now, what we also said we could do for the cross product, instead of, we did all that component stuff on the previous page. See all those components, x, y, z, x, y, z? What we found we could also do, or what we were told, is that you could take the magnitude of the first vector, multiply it, well, first vector is here, multiply it by the magnitude of the second vector, and then multiply it by the sine of theta. That also works, and so let's see what that would give us. If I take the force of 150 newtons, where is r sine theta on my diagram? And r sine theta would be this component right here. So this would be r cosine, this would be r sine theta, and r sine theta is z. So this approach also works, and I'm going to say more often than not, we can solve it this way. In most of the examples that we run into, we can just take the force, multiply by r, and then multiply by the sine of the angle between them. So I think there's a homework problem where they have you plug in all the components. I think it's a good exercise to go through. But I think most of the problems will be using the formula for the magnitude of the cross product here. Okay. And then how do we tell what direction the torque is in? And we use what's called the right-hand rule. Now there's variations on the right-hand rule. The textbook uses one version of this. I had a student show me a different way of determining the direction of the vectors when we're doing cross products. And the student said, look, you put your thumb in the direction of the first vector, and you put your fingers in the direction of the second vector, and then your palm will face in the direction of the cross product. So if I do that, if I put my thumb in the direction, now the first vector, when we're calculating torque, was the lever distance. I put my thumb in that direction. The second vector was the force. I put my fingers there, and my palm is facing in the direction of the cross product, which is the torque, and that's going to be into the board. Okay, so again, there are different versions of how to keep track of this. Find one that you're comfortable with, that's reliable, and practice. So again, we've come back. We looked at the torque version of this, and now what we want to do is also introduce angular momentum as a cross product. It turns out the angular momentum can be written as R vector cross momentum vector. So there's the connection between angular momentum and linear momentum for a particle or for a small object. So if we can treat this object as being, essentially an object with some mass packed into a reasonably compact region, then we can just say, okay, we'll treat it as if it's a point object, and all the mass is concentrated at that point. We can take the mass, multiply by, well, we can actually, this is in terms of momentum, so we can calculate the momentum by taking that mass and multiplying by the velocity. Okay, now they go through a lot of these formulas, and these can get to be a little confusing, and I don't feel like a lot of them are essential for doing the problem solving. Take a look at the homework problems. But let's just ask a couple of, step through a couple of these. So if we take the angular momentum, and we take a time derivative, we take a derivative with respect to time, then what we're going to get is the lever distance crossed the momentum as a function of time. Now the other side of that would be the time derivative of the lever momentum, but the lever momentum would be changing in a more complicated problem. So we're going to stick with this. It's just r cross dp dt. And then this is force. So if we take r cross the force, what that's going to lead us to is torque. So what they're trying to show here is that this side is going to become torque. And so starting from linear motion equations, now what we've done is derived formulas for angular momentum and torque and how those are related. And so they're introducing now a particle, a compact object's angular momentum. And so what they're going to do is say, here's a lever distance, here's the object's mass, it's got momentum. Now the momentum can be left as momentum, or we could write it as m times velocity. In a lot of problems, I'm going to say in most problems that we run into, oh look, it's identical to the page before. Momentum gets written as m times velocity. So this angular momentum as a cross product, r cross p, can be written as m r cross v. And the magnitude is going to be r cross p r times p times the sine of the angle between them. And so the angular momentum here is rp. Now here, again, if it's circular motion, if the r and the p are perpendicular to each other, then it becomes the sine of 90 degrees, which becomes 1. And that says the angular momentum can be written as rp or r times mv. Now we're going to see some examples here in a bit where r and p are not perpendicular. So if it's not circular motion, then we have to be more careful. The vector diagram for this would come from taking the r, moving it over to here. So I moved the r over onto my vector diagram, and then I took the momentum, moved that to my vector diagram. That is the angle between the two of them. In this case, it's 90 degrees, but it doesn't have to be. More generally, it will not be. Okay, oh, and then the right-hand rule. So the right-hand rule, this is going to give me how much angular momentum I have. And then I can do r cross p, so vector number 1 is r, vector 2 is my fingers, and my palm will face in the direction of angular momentum, and that's out of the page for this example. All right, what happens if I have a lot of objects and I add together all of their angular momentum? What happens? Now, one of the examples we could think of is planetary systems. You could take all of the planets and all the moons in the solar system, and you could measure how much angular momentum they all have, and you could look at the directions of the angular momentum. You could add them all together vectorially to get a total amount of angular momentum of all the planets and the sun and the moons that are in the solar system, and other objects too. You could go to the smaller objects and include those. Now, if we're in an inertial reference frame, then we can show that any changes in the total amount of angular momentum, the total amount, would be due to some kind of external torque. Now the internal torques, so planets do exert torques on each other. Planets exert torques on their moons, and the moons exert torques. So all of these objects in the solar system are exerting torques, and they can have effects on each other's orbits, and they can have effects on each other's rotations. Those are all internal. So as long as we can neglect, outside interference from other star systems, then we can treat the solar system as an isolated system, and if angular momentum is disappearing from some planet in the solar system, maybe it's being picked up by a planet somewhere else. So we can look at transfers of angular momentum taking place. Now with our new definition for angular momentum, we have to start looking more and more at these symmetry axes through the center of mass. If I have a cylinder, and we're going to place the origin of the coordinate system right at the center of the cylinder, so that would be a very symmetric object. And the rotation that we're looking at here, we're calling this the z-axis, so we can have rotations around. That's a symmetry axis. If I look at the z-axis, the mass is distributed symmetrically around that axis. And that means that the axis also goes through the center of mass of the object. Now I can take an angular or a lever vector from that center, the center of mass, the 0 point in the coordinate system, and then I can look at where the momentum is for individual parts of that object. So if I take that object, I break it up into a lot of little pieces and add them all together, I could take the angular momentum of individual pieces, add them all together to get the net angular momentum. Sounds like an integration problem, right? Well, when we use our cross product definition, what we can see is that there's a point here. Here's a lever distance out to that point. It's moving in that direction. Its momentum is going to carry it around in circular motion. When I do the cross product, the angular momentum is pointing in a funny direction. So the angular momentum is not pointing along the axis of the angular rotation. That means that this point by itself is not a symmetry, would not produce a symmetry axis of rotation. It's not balanced. So what we can do is say, yeah, but for this cylinder, there's going to be another object over on the other side, and by the time I've taken objects here and here, symmetrically placed in the other direction, and then matching symmetrically placed objects here, all of the angular momentum of all those will actually balance out and point in a manner that it points along the rotational axis. In fact, all I really need is just one more object over here, and there are two angular momentum vectors. If I add them vectorially, now point along the rotational axis. So this is an important concept. So here's an example of something where we're trying to rotate this mechanical structure around an axle. Here's an axle, here's some bearings, but what we've done is we've placed the masses so that they're not symmetrically placed with respect to the axis of rotation. If we tip these so that they're both like in a horizontal plane, then their angular momentum would add up in a manner where it would match the omega direction, but currently it's not. And what that tells us is this: if we do an angular momentum assessment on an object like this, and it doesn't line up with the axis of rotation, then what that tells us is that we are going to have torques constantly acting on this object in order to have it stay rotating along the axle. So, you know, if I'm having my tires balanced or my wheels balanced on my car, what we're trying to do is get the tires and the wheels such that there's a symmetry around their axis of rotation, so that when we rotate this, it's not going to wear out the bearings on the car. The wheels will naturally rotate in the direction of the, you know, when the car is driving and the wheels are rotating, it naturally rotates around that axis instead of having to have a constant force or torque coming from the bearings in order to keep the wheel rotating in that direction. So, you know, this is balancing, making sure that the objects are balanced. Okay, I think that's, just want to make sure we've said everything we wanted to say on that. So let's take a look at some of these rotational systems. Now, this could be analyzed in terms of angular momentum, but I guess I went back and used linear momentum on this. We could have done it all on angular momentum. Let's take a look at this. What we've got is we've got a pulley, and we've got an object hanging on this side, we've got an object hanging on this side, we have a string or a cable that comes up and over, and the cord is inelastic, which means it doesn't stretch out, and it's negligible mass. Now, the objects with significant mass that we have to consider is object A, object B, and the pulley also. So I guess I turned this into kind of a chapter 10 problem, and I think that's fine. I think we're going to be fine doing that. Anyway, what we want to do is we want to set out to calculate the acceleration of the system. Now, if we let go of this, what likely will happen is we're going to tend to get the heavier object is going to be, we're going to accelerate in that direction. So there's a gravitational force. There's a gravitational force acting on each of these objects, object A and object B. Both have a gravitational force acting on them. And the heavier object will result in the larger gravitational force, and that says that the acceleration will be in that direction. Well, if object B has an acceleration in that direction, object A is going to have an acceleration in an opposite direction here. So object A is going to have an acceleration here. And then the other acceleration that they kind of, I feel like, left out is there will be a tangential acceleration. If I pick a point on the pulley and follow it, that point on the pulley will be undergoing a tangential acceleration. And the entire pulley will be undergoing a rotational acceleration. So let's see what this looks like. So we got a pulley. We've got a couple of masses on here. Here is the string going over. Now there is friction between the cord and the pulley. And so the pulley is going to be set into motion. And it's static friction, so there's no sliding that's happening as a result. But we'll say that this is a tangential acceleration along the edge, and that, got to see how we're going to bring these formulas together. Okay, so right here, the tangential acceleration along the edge of the pulley is going to equal r times the angular acceleration of the pulley. So that's going to be key, because what we've done is we've got a couple of objects in linear motion, we've got the pulley in rotational motion, and so the rotational motion is going to come from, maybe take a look at this first, the rotational acceleration of the pulley depends on the torques and the rotational inertia. Now if I take a look at this diagram, what forces are acting on the pulley? And we've got a force of gravity, mg. We've got a normal force. So this pulley is sitting on an axle. So the pulley is, it's mounted onto an axle, and then it's being pushed upwards by a normal force, a contact force. Well, that's not going to create a torque because it goes right through the axis of rotation. Mg is not going to produce a torque because if it's a uniform pulley, the center of mass is right at the center of the pulley. That's not going to create a torque either. So N doesn't create a torque, Mg doesn't create a torque. I drew them in for completeness, but we don't need them to analyze the rotational motion of the pulley. So the forces we do need is that there's a tension 1 on this side, and yeah, I switched the A's and B's into 1 and 2. There's a tension in this direction, this cord is being pulled down by this object, and there's a tension set up here by the presence of this object. So there are these competing tensions in the cord. Now each of those tensions, when I multiply it by the lever distance r, is going to give me a torque. So torque 1 over there is T1 times r, and torque 2 is T2 times r. So here's torque 2. Here is the lever distance. That's perpendicular, so I can just take the force times r, and that will give us the torque. So that's what the torques are going to be given by. Now, I always end up taking the rotational inertia I and replacing it with cmr squared. If I have a round object, it's handy to, we've found out in other examples, to write it in terms of the shape factor, so that's what I've done. And then what happens here then is I can factor out an r. I've got a couple factors of r here, and then I can start to cancel factors of r. Now one more factor of r comes in here. When I go from a rotational acceleration to a linear acceleration, I pick up another factor of r, and that says that for this rotating object, the tangential acceleration along the edge where the cord is located can be written as T2 minus T1 times big R squared over shape factor, mass of the pulley, times R squared. So I can get both factors of R to cancel. And that says that there's a relationship between the two tensions, the mass of the pulley, and the shape factor. Now, is it a cylinder? Did they say it's a cylinder? It looks like a cylinder. Maybe C is equal to 1/2. But that's going to determine what the acceleration is. So there you go. There's a formula relating the acceleration to the two tensions and to the mass of the pulley and the shape. Now, I wrote it two different ways. I wrote it in terms of acceleration, and then I also wrote Cm acceleration is equal to T2 minus T1. And that last version of the formula is written there because what I know I can do is, by looking at the linear motion, I can get an expression for T2 and T1. So let's do that. So for object 1, there's an acceleration we decided would be upwards, and that acceleration is going to be driven by T1. As far as this object is concerned, T1 is pulling it in that direction. That would be T1 minus the gravitational force, because it's in the opposite direction, divided by M1, and from that I can get an expression. So that's how much tension we'll have on the left side of that chord. Now on the right side, over here with M2, same idea, except that the acceleration now is downwards, and that says that M2G is in the direction of acceleration, and that T2 is opposite. So that picks up the minus sign. And then that gets divided through by the inertia. So the inertia factor also comes in there, and that allows me to calculate, or not calculate, but to derive a formula for tension 2. So what we can do now is we can take, according to what we solved rotationally, T2 minus T1, I can plug in right here. So these are involved problems, and I hope that you've, as we go through these in different chapters, you can see that the complexity it's increasing, and so make sure that you step through these problems a few times until you're comfortable talking yourself through. This is a good example to maybe pay some attention to. So here is the pulley. It has properties of M, its mass, its shape, its rotational inertia, and this R. And those are all related, but those are kind of 4 items that go along. I've dropped out the mg, I've dropped out the gravitational force on the pulley and the normal force on the pulley because they weren't producing any torque, so I cleaned up the diagram a bit. So what we can do, on the last page, we were left with CMA is equal to T2 minus T1. And now I've substituted in that expression for T2, and here was the expression we got for T1. So putting all of those together, I can see I've got factors of A on the left side. I have a factor of A here, I have a factor of A here. I can take those terms, bring them to the left side, factor out the A, and everything on this side becomes A, M1 plus M2 plus C times M. On the right side then, I can bring over, oh, it's on the right side already, never mind. M2G minus M1G is all that's left on the right side. So, always check these to see if they're making sense, if the algebra is making sense. What this is saying is that the net force driving this system is M2G minus M1G. So we can think of that as a net external force that is producing the acceleration of the entire system. It's not just producing the acceleration for these objects, it's producing the acceleration on the pulley. Now, the total inertia in the system is the masses of the two linearly moving objects, M1 and M2, and then the pulley's mass times the shape factor tells us how much inertia the pulley will contribute. So, we could ask what would happen what if the pulley's massless? Or what if the pulley's mass is so low that we can treat it as being negligible? Well, if Cm is much, much less than M1 and M2, this equation can be approximated by removing the Cm. Oh, look, and then it's chapter 4. So that takes us back before rotations when we didn't know how to include the effect of the pulley. So we kept saying the pulley is massless, the pulley has negligible mass, but now we know how to take that into account. All right, let's take a look at a couple of other kind of interesting examples here. Maybe you've seen some of these demonstrations done. What they're saying is you're holding a bicycle wheel, and if it's not spinning, and you take a bicycle wheel and you try and tip it up, that's what they're doing here. So you take a bicycle wheel and you tip it up and it moves upwards. But if you take a bicycle wheel that's already spinning and you tip it upwards, it doesn't go up. It goes to the side. So that's weird. Now what's going on here is when you have a bicycle that's spinning, there could be a lot of angular momentum built up. That's going to be based on how much mass the bicycle wheel has, how large the bicycle wheel is, and how fast it's spinning. But if you've got a bicycle wheel, especially one moving very rapidly, you could have a fair amount of angular momentum built up. Now if it's not spinning, you don't have the angular momentum, and so wherever you try and tip it, it follows that direction. But if it's already spinning, then the torque that you exert on it is going to end up redirecting the angular momentum. So let's think about this. Torques could either speed up a rotating object, a torque could make it spin faster, a torque could slow it down. A torque could take a spinning object and slow it down. A torque can also change the direction of the rotational axis. And that's what happens in this case. If the bicycle wheel already has angular momentum built up, then a torque, tipping it like this, it turns out that's not going to speed it up, it's not going to slow it down, it's going to redirect the angular momentum to the side. And you actually end up with something called precession if this process continues. So here's one way of thinking about this. Here's the moon, here's the Earth, here's the moon. The moon starts out with some linear momentum. So let's do a linear, this is our linear momentum example, side by side with an angular momentum example. Now in this example, there's a force pulling the moon towards Earth. Now what would happen if the moon had no momentum to start with? Well, if the moon had no momentum to start with, and suddenly a gravitational force pulls on it, the moon will begin moving in the direction, it'll start picking up speed in the direction of the force. But instead, the moon already has linear momentum built up in a direction perpendicular to the gravitational force. So if it already has momentum built up, what the force will do is it will redirect the momentum. So dp, this infinitesimal piece of momentum, is going to be in whatever direction the force is in. And that's why when we write, force vector is equal to dp dt, or here's maybe a better way to write it, changes in momentum, specifically the direction, and magnitude, depend on the direction of force. The changing momentum will be in the direction of the force. And so what happens here is, since the momentum is already here, but there's a force that's perpendicular, the momentum gets tipped. And that's what happens in circular motion. So here is the momentum that we started with. The force acted sideways, and what the force did was created an additional change in momentum. It created a dp in that direction. Now, if this is an infinitesimal dp, then the angle here is going to be an infinitesimal angle. We'll call that d theta. That results in circular motion. So as the moon orbits the Earth, its momentum keeps changing directions. Now again, what we can do is we can take all those individual momentum vectors and put them onto a vector diagram and see that the momentum goes around in a circular fashion as the displacement does also. Now the linear analog to that, we said, what about the bicycle wheel? Well, here's a bicycle and it's already spinning, and so what's happening here is it's got angular momentum built up in this direction. So when we exert a torque, when we tip this, the direction of that torque is actually sideways. And so we can just write the equations down kind of side by side. Initially the angular momentum was along the x direction, and then the torque was applied sideways, and that redirected it. Now this is saying it's a top view. So, and this is a bicycle, see the tread? That's a bicycle wheel, and then those are the handles that that person was using to hold on to it. But it's a top view. We're looking down on a bicycle wheel that's rotating in a vertical plane. And what will happen is if we create a torque in this direction, if we tip it along this axis, so there's the torque, that says when we tip it, if we push that handle down and lift this one up, that's creating a torque in this direction, and a perpendicular torque will create an effect called precession. So the bicycle wheel rotates, it goes around in a circle, okay? So it ends up going in a circle instead, and it's called precession. Now, this is one of those situations where the math predicts this, but I look at all the diagrams and I think, nah, it's not really going to happen, is it? But it does. You know, when you get these bicycle wheels, and you know, you guys learned to ride a bicycle at some point, and part of the difficulty in learning to ride a bicycle is learning how the torques, when you turn the steering wheel, that's creating a torque on that rotating bicycle wheel, and the bicycle wheel doesn't respond the way that you would initially expect. So learning to ride a bike is kind of like, you know, trial and error, trying different things to keep yourself balanced. And at some point it works. Whether you can explain what you just did or not, when you learn to ride a bicycle, it works. So here it is. Remember, you'll never forget how to fall off a bike once you've done it once. So you'll always remember how to fall off a bike. Or ride a bike, I guess that's the saying. You'll always remember how to ride a bike. So here's a person, again, it's a top view. We've got these bicycle wheels going around in a vertical direction, and the bike as a whole is headed in this direction. See, they got their helmet on. Good idea. Always ride with a helmet. Now, the bicycle wheels are spinning around, and so if I use my right hand rule, I can say, oh yeah, it's a symmetry axis for the wheel, and the angular momentum is going to be right along the axis of rotation, because I have my bicycle wheels perfectly balanced, so the bearings are not going to, you know, get stressed out, and the angular momentum will be right along that axis. Now, when I learned this in my freshman physics class, it was really confusing. These arrows that were going to the side, you know, I'd ride my bike. I was riding my bike around everywhere, and so I'd ride to campus, and I'd start thinking, remember that physics lecture? And I would see these arrows going to my left, and I would crash. You know, I would go, oh no, I've got these arrows going this way, and then I'd fall over. These vectors that represent rotational quantities, I think we mentioned this, they're sometimes referred to as axial vectors, or also they're referred to as pseudo-vectors. Now, most of the vectors that we've looked at so far, I'm going to say, you kind of have an intuition for, you know, the direction of the vector means something. Well, here it means something too, but what it's oriented to is the axis. So one way to think about this is, rather than putting this arrow over here, first of all, bring the arrow to here and to here, so it's balanced. Otherwise, I'm going to fall off my bicycle. And so, and then the other thing was the direction of the arrow. And as you've probably recognized, it's just arbitrary. It just turns out that when we have rotating objects, the axis of rotation provides us all the information about how that object is oriented. But to use a vector, we have to flip a coin and go, okay, am I going to use right-handed rotations to be positive or left-handed rotations? And by convention, we decided to go with right-handed rotations. So we could just as easily have defined these rotational vectors as going in the other direction. So finally, once I realized that, I made my peace with the axial vectors, and I stopped falling off my bicycle at that point. Pretty much. I guess I still fell occasionally. But it's just arbitrary. So what I did was, when I was riding my bike, I stopped thinking of this as an arrow, and I just thought of it as angular momentum along an axis. So I just thought of it as a balanced axis, and that saved me from crashing on my bicycle. All right, so here's this person riding the bicycle, and they want to go to the left. So what do? You lean to the left. Now, when you lean to the left, what happens is the gravitational force now doesn't line up with your contact point. So let's go back before you started leaning. Here's a gravitational force. It's coming from the center of mass. And it's directed, and it's right over top the contact point. Now in the diagram, they used mg. I should have crossed that out and put in normal force. But the normal force will have the same magnitude as mg, right? So we've done enough force diagrams. So here is the normal force lifting up on the bike. When the normal force and the gravitational force line right up, there's no torque. That does not provide a torque. But when you lean to one side, there is a torque produced. And the torque, let's see, is tending to rotate the object over. So this torque is tending to pull that person over and crash them, right? So the torque is coming out of the page, and that's because here is the lever arm. So here is the contact point. We have I did write in axis, that's good. So the axis of rotation here is the contact point of the bicycle wheel. So here we have this contact point. We've got a lever vector that points in that direction. So it's pointing here. And then a torque is being provided by gravity. The normal force, that's not mg, it's the normal force. The normal force is not providing a torque because it goes right through the axis of rotation. But the gravitational force, mg now, has a lever distance here. And if we use the right-hand rule, it tells us that the torque is coming out of the board, and that's tending to rotate the person in the positive direction, which is going to have them crash on the street. Now, fortunately, this person is not at rest. If this person was at rest and they lean to the left, they just crash, right? It just rotates over. But fortunately, this person is riding along, and the bicycle wheels have already built up a lot of angular momentum. And so once you have angular momentum already built up, when a torque shows up, the torque redirects the angular momentum. So what's going to happen here is this. Here is the person, hands on their handlebar. Here is the direction of the angular momentum. They lean to the left, and that produces a torque in this direction. So this is the omega here. The omega here is for this rotational axis. The torque is this direction here. So we saw that from the picture down here. The torque is going to the back of the bicycle rider. And what that will do is it will redirect the angular momentum and rotate it. Oh, it's going to help me make a left turn. So that's how it works. So somehow when we learn to ride bikes, we learn that, turning the wheel in this direction, not only, it's a couple different things going on here. First of all, if you're starting to fall to the left, you turn the wheels in that direction so that you can regather your gravitational force over the wheel. You want to keep your gravitational force over the wheel to be able to balance. But when it comes down to actually turning, I'm already moving and I want to turn, leaning to the left redirects that front wheel, and it helps steer you into the left direction. Okay, everything reverses for the right. So if I want to make a right turn, what do? I mean, these vectors are the same. If I'm going forward, those vectors are off to the left. Oh no, off to the left, now I'm going to crash. So these vectors are pointing off to that left side. If instead I lean to the right, then the torque direction, R cross mg, is going to be into the board. There's going to be an X here into the board. And what that will do is redirect the angular momentum vector so that the wheel rotates to the right. Okay. So again, these torques are not making the wheel spin faster or spin slower. They're redirecting the axis of rotation. Pretty cool that angular momentum, the Newtonian physics predicts all of these things. And we go out and try them, it really works. All right, we are back to a statement that the book keeps coming back to, and it's fine. It's just restating that the angular momentum of a system is constant unless there are torques acting on it. So an object or a system of objects, the angular momentum will be constant. I guess that ties in with this. So what happens is, if there's no torque, if I'm maintaining, my vertical orientation on my bike so that the mg force is right over the normal force, then there's no torque, and actually the faster my bicycle is going, the more angular momentum that's built up, the easier it is to balance on a bicycle, right? You guys know that. As you go faster and faster, you can take your hands off the handlebars, right? Because there's enough angular momentum built up. And then, even with your hands off the handlebars, right? So I can take my hands off the handlebars. I don't need my hands on the handlebar to turn. Because why? What do? Lean to the left. If I lean to the left, the torque produced by the gravitational force will turn the front tire for me. The wheel will turn to the left as a result of the torque. What happens if I lean to the right? The torque produced will reorient the front tire so that it's angled off to the right. Riding a bicycle. So let's see, there's a couple more examples here. This I'm going to say is non-essential as far as, I don't think we have any homework problems related. It's kind of interesting historically. So, in astronomy, and discoveries in astronomy, Johannes Kepler played a pretty major role in trying to understand planetary motion. Now, there had been astronomers from thousands of years before in Greek and Egypt who had already, groups of astronomers who had determined that the Earth was orbiting the sun. But people had a counter-argument to that. They said, look, if the Earth is orbiting the sun, then as the Earth orbits at different locations, the pattern of stars should look different. And when they looked at the stars to see if you could see any shift in pattern in the stars, you couldn't see it. Now, we understand now that the reason that was not observable is because the stars are so far away, the shift is unobservable. But we now, since the mid-1800s, we have instruments, telescopes and measuring instruments that are able to detect Earth's orbit by looking at stars and seeing how the stars shift back and forth. The pattern of stars shift ever so slightly as we're orbiting the sun. Well, anyway, in kind of the history of astronomy, the astronomers who had already established that the sun was at the center, then kind of got pushed to the side because, again, the argument was, by all observations, it certainly appeared that the Earth was at rest. And so when Kepler came along and picked up on the ideas of Nicholas Copernicus, kind of proposing this heliocentral model, Kepler spent years and years going through data that not he collected, but that was collected by Tycho Brahe, a Danish astronomer. Tycho Brahe had spent years and years and years carefully collecting data on planetary motion. And so Kepler just did the math. Kepler picked up all of those observational data and was actually able to make predictions about planetary motion. Prediction 1, the planets are not going in circles, they're going in ellipses. Okay, Copernicus had the planets going in circles, and that meant that the observations were off, from Copernicus's theory. Kepler corrected that and said, no, they're ellipses. Once you move to ellipses, it matches the observations. The second thing that Kepler found out was that the planets didn't move at a constant speed. They were following slightly elliptical orbits, not terribly elliptical. I mean, they're almost circular, but these orbits had an elliptical nature to them. and that the sun was located not in the center of the ellipse, but the sun was located at one of the focuses. We talked about this a bit in chapter 6. So Kepler actually found out that the planets go more slowly when they're away from the sun, and then they pick up speed and go faster, and their fastest point is their closest approach to the sun. Now, today we would say this is a gravitational effect, right? So as the planets move away from the sun, gravity is slowing them down, and on the way back, gravity picks up the speed. Kepler was able to determine that the area swept out by the planets. So, you know, these people were amazing mathematicians. They could go in, this is not pre-calculus, but pre-calculus, before calculus, and Kepler showed that equal areas were swept out in equal times. So that meant when the planet was farther away from the sun, it traveled shorter distances, and there's a certain amount of area. And then when the planet was traveling closer to the sun, it would sweep out an equal amount of area. So it would travel longer distances. And we can actually go back to this definition of angular momentum. So this is, okay, that was my best attempt at an ellipse. So here's the ellipse. The sun is located not at the center, that's key, not at the center. It's at one of the focuses. There's another focus here, but there's no object there. So the sun is located at one of the focuses, at the other focus, there's nothing there. And using Newtonian physics, using the idea of angular momentum conservation and gravitational forces, you can rederive all of these laws, the Kepler laws of planetary motion. Now the one we're looking at is angular momentum, which we said is mr cross v. Now in terms of a magnitude, that would be mrv sine theta. Now up until now we were looking at circular orbits, and theta was 90 degrees and the sine of 90 was 1. But now it's no longer a circle. And so we can take a look at this ellipse. Here is the sun. Here is the planetary motion. Now the planetary motion is tipped. So I'm going to call that distance dr. And these sides are, well, if that's dr, where dr is a really, really short distance, then I can treat the two pieces on the side as if their lengths are the same. So I'll call this r and this r. Now dr is in the direction of the planet's velocity, and dr is equal to the velocity times a short time interval. The area that a planet would sweep out in its orbit would be the area of, I hope you guys have seen this in calculus, this sector can be treated as a triangle. So in the limit, where dr is really, really, really small, and dt is really, really small, I can turn that into a triangle with two sides that match. So the area of that triangle, the dA, would be 1/2 times r times dr sine theta. And here's why we need the sine theta. Coming over to this diagram, here is the lever distance. Here is the velocity of the planet tangent to the orbit. Now, there's, I didn't get that drawn. It seems, it's not bad. So this component of the velocity is the perpendicular component. So to get angular momentum, I just want the perpendicular component of velocity. I don't want the total velocity. So I'm going to take the velocity, divide it up into cosine theta and sine theta components, where theta is the angle between the r vector and the v vector. So following our cross product rules, this would be mrv sine theta, because I only want to keep the component that's perpendicular. Okay, and that falls right out from the definition of a cross product. So what happens then is this, that dr is in the direction of the velocity, but if I use this to finish off my triangle, it's not symmetric. And so what I have to do is take the perpendicular part of the velocity so that I can have this triangle be given by 1/2 r dr, not dr, but this distance right here and that distance right there is dr sine theta. So the area, dA, is equal to 1/2 r. Now we said that dr is equal to v times dt, so I've substituted that in. What it says is that d area, d time, the amount of area swept out during a certain, any amount of time, is given by 1/2 r v sine theta. And if you compare formulas, r v sine theta, that's the angular momentum. So Kepler's law that he came up with, saying that planets sweep out equal areas in equal times, can easily be derived from angular momentum conservation. So in Newtonian physics, if you have an object located at the center of a coordinate system, and you have what are called central force, that object at the center is pulling on the surrounding objects right towards the center. If that's the case, the torques on the object will conserve angular momentum. You will not have torques acting on the object around that point. There's no torque around that. And so as a result, because the R is here, and the force is right back towards the center, so R and F, R is pointing back towards the sun, R and F are in opposite directions, and they won't produce a torque. So if there's no torque, angular momentum needs to be conserved. And what this shows is that angular momentum conservation for an orbiting object is equivalent to having the area sweep out at a uniform rate. Okay, let's move on from that. You guys can go back and take a look at that after. I do want to get into a couple of these later examples. So here's an interesting example. Let's say that we fire a bullet, and the bullet is zooming along and hits the edge and stops. It runs into the edge of a rotating cylinder, they say. So here it is with the cylinder. The cylinder was at rest, but you can imagine if that bullet hits, it's going to transfer something. It's going to have an effect. It's going to exert a torque on that cylinder, and that torque is going to start, the cylinder is going to go into rotational motion. So let's set this problem up. We've got an object M coming in. Now there's a fixed axis in this problem. So there's an axis and it's fixed, and it's right at the center of the cylinder. And it's an inelastic collision, and it's going to set the cylinder into motion. We want to find out what the speed of rotation will be when the cylinder is put into motion. Now what we can do, and this seems a little crazy, but we can say that this object, which was traveling straight, actually has angular momentum. It's kind of like anticipating what effect it's going to have. So we can take its momentum, m times v, and we can look for a perpendicular lever distance, which is r. So m times v times r is the angular momentum of the object when it's coming in. Now, it's going to hit and stick, and so we're going to have this attached to the edge, and it's going to rotate around. You know, another example I always think of here is it's like an asteroid hitting the Earth. So here's Earth, and here's the asteroid coming in. I mean, in Earth's case, it's already rotating. But what effect would an asteroid have that hits like this on the rotational velocity of the Earth? Anyway, here is the bullet coming in. It's got an angular momentum, mvr. Afterwards, we can write the angular momentum as I omega. This is the rotational inertia. So what's going to happen is the cylinder, or the sphere, or the hoop, has a rotational inertia of cmr squared, and a mass, an isolated mass, a point object, has a rotational inertia of mr squared. So those are the rotational inertias of the two objects. We can take the before angular momentum, set it equal to the after angular momentum, and solve for omega. And that tells us what the rotational velocity will be after this object has hit. So that's a pretty good problem. That's another one that I'm going to say make sure that you take a look at that. All right, let's also look at the kinetic energies. So the very same example before, the bullet coming in had kinetic energy 1/2 mv squared. Now once it goes into rotation, we can write the kinetic energy of rotation as 1/2 I omega squared. Now the question is the energy going to be conserved? And I'm thinking it's not, and that's because it feels like it was an inelastic collision. The object came along at some speed and it hit and it stopped. It didn't bounce off, so they're not separating. So let's see how much kinetic energy is lost. And so the kinetic energy after 1/2 I omega squared, I've substituted in the expression for the rotational inertia, and then I substituted in the expression for omega and squared it. And so then I factored out, I realized I have a factor of m, a factor of 1/2, and a factor of v squared. I factored all that out, so I've got the rotational kinetic energy as 1/2 mv squared times that factor. Now when I factored out the 1/2 mv squared, it really simplified. I guess first of all the r's canceled. So the r squareds here and the r squareds and the r squareds, those are gone. And then I took out a factor of m here, took out, this is what we were left with. And then what I can do is I can do a ratio. So if I take the kinetic energy after divided by the total, what portion of kinetic energy remains? And it depends on m over m plus cm. So if m is just really, really tiny, then most of the kinetic energy will be gone. Okay? If little m is really, really big, and somehow it runs into something that has very little mass, then most of the kinetic energy would be conserved. Okay? And so there's going to be thermal energy generated from the impact. All right, the last couple topics, again, these are a little beyond what we're really interested in for a midterm or something, but they're kind of fun to think about. The tops work kind of the same way we described with the bicycle. So we identify for a spinning top, it's tipped to the side, so the top has tipped over a little bit. It's got angular momentum and its angular velocity tipped to the side, and then it goes into precession. Okay, so it ends up precessing, and you guys have seen tops that are spinning. So they don't tip over. Instead of tipping over, they precess. So kind of an interesting effect with this. And then here is the diagram. So we've got the rotational velocity vector. We've got the angular momentum vector. Now the angular momentum vector, when it's tipped, we've got mg. And then there's a torque lever distance here. If r measures from the axis, we're going to measure everything around. So the axis we're measuring around is where the top is in contact. And then when we come up to the center of mass, this is where the mg force is applied. Here's the normal force here. So we're going to have a lever distance of r sine theta and a torque, a gravitational torque, given by mg r sine of phi. Now, if we do a top view, so this is a top view here, let's measure the precession going on. There is, from this picture, there's an L cosine phi right along the z-axis. We're not looking from above yet. And then there's a sideways angular momentum, and that's L sine phi. So we can look at the angular momentum and relate it to the torque. So dl, the rate at which the angular momentum is varying, is torque times dt. And from what we looked at gravitationally, the torque is mg r sine theta. We'll add the factor of t in here. So there's going to be a precession rate. So omega, this is capital omega, this is keeping track of how rapidly does the precession occur for a top. That turns out to be d theta dt from the diagram that we have here. This is keeping track of a top view of precession of my top. That's going to be given by dl over L sine phi dt. I can put the torque of the gravity, the sine of phi cancels out, and the prediction is that the top will precess at a speed given by mgr over I omega. So it depends on the mass of the top, it depends on its rotational inertia, depends on the gravitational field, the dimensions, the center of mass location on the top, and how fast it's spinning. So if I can get my top to spin really fast, the precession is slower. So if the top's going really, really fast, then the torque has a more difficult time redirecting its angular momentum. So when you get things, a lot of angular momentum built up, it's harder to redirect that. So that's our gyroscope example. And here's another example that we definitely want to take a look at. What happens if you're on a rotating platform? So if you're on a rotating platform and you throw something, well, it goes in a straight line as observed from an inertial reference system. But for the person on the rotating platform, it appears that the ball is going sideways. Now the reason it appears that the ball is going sideways is because the platform is rotating. So here is the inertial reference frame. The platform is rotating. The person throws the ball in this direction and it goes in a straight line. Now, from the person's viewpoint, the surrounding world is moving around the platform, and as the person starts to rotate away from the path, they interpret that as the ball, or the object that they've thrown, is moving away from them. Okay. So it's important to be able to go into the inertial frame. This would be the inertial frame of the surface of the Earth, and watch the ball go straight, and then we can analyze what's going on in terms of what does it look like the ball is doing. Now, the Earth itself is a rotating platform. It's a little more complicated because it's not a flat rotating platform, it's a spherical rotating platform. So let's do this. Let's just go back to a flat rotating platform. And what we can do is we can analyze what just happened here. In the inertial frame, what's going on at different locations is as I move away from the center, that location is moving faster and faster. So if someone at point A throws an object, they throw a ball off in that direction, what happens then is the points A and B continue to rotate. This faster point B, is going to move beyond where the ball is located. And so instead of the ball appearing to follow that path from A to B on the platform, from observers on the platform, the ball in their coordinate system is moving away from what they're calling straight line motion. So in accelerated and rotating coordinate systems, that can confuse things. And so when we're launching rockets, for example, we have to, if we're launching some rocket and it's going to, take off and the booster is going to land at some point, we have to take the rotation of the Earth into account as to where that's going to happen. Now here's an example with the rotating platform that we can take a look at. Let's imagine that an object, maybe it's you, start walking along the platform at a steady velocity. Now the platform is rotating, so that says that as you move along, you're actually going to be pulled to the side. So let's say that you're moving away from the center, and that your location is given by v times t, and that it's spinning at a steady rate omega, and so the theta angle is given by omega t. So this is reasonably straightforward motion. What that's going to do for us then is, it says that the x-coordinate, if I think of point A, the x-coordinate is given by r cosine theta, the y-coordinate is given by r sine theta. And I can replace the r with v times t, and I can replace the theta with omega times t, and then we can do everything within an inertial reference. So we can step back and observe this rotating platform and find out what happens. Now what we're already expecting is, if this person is moving, away from the center and then also rotating, what's going to happen at the location where they're, standing at some point? They are going to have a velocity outwards in the radial direction because that's where they're walking. Now they're also going to have a sideways component, and notice that as they get farther away from the center, that sideways component is increasing. It's getting bigger. They are going to have to be picking up speed in that lateral direction. That says they are going to have a tangential acceleration if they're going to stay attached to the platform, right? They got the platform, they drew a line, they said, I am walking that line. If they're going to be able to keep walking that line, they're going to have a sideways, a tangential acceleration. Now what they're also going to have, as a result of rotational motion, is they're going to have a radial acceleration back towards the center. So if they're going to stay attached to the platform, they're going to have accelerations here and here, and they're going to need forces to allow them to maintain those accelerations. All right, a couple things to point out here. We decided the person is walking at speed v, and if we remember, the radial acceleration is r, given by r omega squared. Now what we can do is we can take our coordinates here, x and y, going back and using rectangular coordinates. That's always a good, kind of a safe way to approach some of these problems. So we're going to go back to using an xy coordinate system, and what we'll do is we'll just take a few derivatives. So what I can do is I can take the x and y formulas and take dx dt to get the x component of velocity and dy dt to get the y component. Now when I did that, I got a set of components that correspond to the radial velocity. So these components, x and y, correspond to the person walking away from the center. Now what this gave us, if I go back and take a derivative and use the product rule, I'm going to get another set of terms, and when I look at these, this actually is sideways velocity. That's the velocity that we have in the tangential direction. And if you remember, velocities in the tangential direction are given by r omega. Now that's the velocities, and that's already a little challenging. What if we do one more derivative to get the acceleration components? So if I take a derivative, time derivative with respect to a time derivative of vx and a time derivative of vy, well, here I only have one time dependence is here, time dependence is here. But here I still have two, I still have to use the product rule. So taking the derivative, I get the time derivative of this expression. Now here, one of the product rules terms gives me a second contribution to that. And then there's finally an extra term out here that depends on omega squared vt. Now remember, vt is r, so this is r omega squared, and these terms are the radial accelerations. Now this is referred to as the Coriolis acceleration, and that's what we're trying to get to here, is if you have motion along a rotating platform. We've already talked about radial acceleration, and that appeared when we carefully went through and did our derivatives. But we're getting what may have been an unexpected tangential acceleration. We talked about this, and it's called the Coriolis. And what we can do is look at the coefficients and say the Coriolis acceleration is given by omega v plus omega v. There's two contributions, which is kind of interesting. And the Coriolis effect shows up in like geography classes, where they say as as winds, as weather travels towards the north or towards the south, it's moving into regions where the surface of the earth is going faster. And so you'll end up with the air either getting left behind or picking up speed. And so what happens then is you end up with creating, as the motion of the air comes in, you end up creating rotational motion due to the Coriolis effect. And I think that's the end of the chapter, and I think that's a good thing because I think we're over time a bit. I just wanted to go back on this example and ask, why is it 2? Why is the Coriolis acceleration 2 omega v? Well, we picked up a factor of omega v from taking the derivative here of the radial velocity, and we also picked up a factor of omega v from the tangential velocity. So that's, I think it's kind of interesting, that what's happening is we've got two velocities going on, and as this velocity happens, we are heading into regions where we are going faster and faster. And so we're picking up an omega v due to this motion, and we're also picking up an omega v due to the tangential effect. So both of those end up contributing to the overall Coriolis acceleration. Okay, and that's, again, that's one of those topics in the chapter. It's a little bit beyond. I wouldn't expect anything in the midterm. In fact, I'm not sure if there's any homework problems looking at Coriolis. Just one of those things that's kind of, oh, actually there is one. There's one homework problem where you do have to go in and look at Coriolis effects. Anyway, whatever questions you guys run into, let me know. Stop by office hours. We'll get those looked at.